Sorry about that. Somebody had a question. Okay, so we were going to graph now these negatives, right? So at 5 pi over 4, we're going to go to negative about negative 1.4, I can't talk. So about here, at 3 pi over 2, it's negative 1. 7 pi over 4, it's again that negative 1.4. And so then what we end up with is just kind of like, looks like a parabola opening downward. So this right here, like kind of one up, one down. I know this isn't drawn great. That is one period of the cosecant. So the period is 2 pi, just like the period of sine is 2 pi, the period of cosecant. So it's not just how long does it take for one little branch, we call them, to happen, but both branches. Okay, and then this would keep going. So we could keep drawing, like we could have another branch here, right? There would be another one like over here and so on. Okay, so that is our cosecant. And then if we think about what's the domain, what's the range, we already talked about domain. Range are the possible y values. That it starts at like 1 and goes up forever, and then at negative 1 goes down forever, but none of these y values between negative 1 and 1 are included. So for our range, we could say y is bigger than or equal to 1 and y is less than or equal to negative 1. Intercepts, like where does it hit the x and the y axis? It actually never does for the cosecant. All right, so now let's move on to the graph of the secant, which is going to look very similar to the cosecant because the sine and the cosine look very similar, except for one that's a translation of the other by a half pi. So again, I have all these cosine values from my unit circle. I have my cosine function just to sketch in here. Notice I just did it as a dashed curve because I didn't want it to look like it was part of the secant graph. Okay, so at 1, if I take the reciprocal, it's 1. So this is negative 1, this is 1. At root 2 over 2, if I flip it, it's the same as on the last one. It would just be 1.41. Here it would be negative 1.41, negative 1.41, positive 1.41. And when the cosine is 0, it's going to be undefined. And so we're going to have asymptotes again, but they're going to be now at pi over 2 and 3 pi over 2. So see, they're happening, and it's just the same thing with the cosecant. It's happening when the sine or the cosine hits the x-axis. That's when you have the asymptote. So that's how I can look at this and really easily know where those are going to be. And it also continues. I have this drawn also here on the negative side. Okay, and then when I go to graph, it's really going to be the same shape, right? And you can see that just by these points, they're the same thing, right? So if I graph, at pi over 4, or 0 is 1, right? So I graph here, and then I graph, here-ish, right? And it only looks like, oh, it's only that little part, but it does continue on to the other side. Right, so and notice they're intersecting each other. There's intersecting each other at that point, at that maximum or minimum. So I can just kind of draw this branch in. So there's one cycle of our secant. The period is 2 pi again. The domain, now the domain, it's anything except for these, I like to call them like the odd multiples of pi over 2, like 1 pi over 2, 3 pi over 2, or happening at 5 pi over 2. So anything except for, instead of writing odd multiples of pi over 2, how we can describe that is we say at the first positive time we have an asymptote is a pi over 2. And then the distance from this to the next time it happens is a distance of pi. So we could say then plus pi n. We saw that happen a little bit back in chapter maybe 2 or 3 when we were solving equations. So then the asymptotes are x equals pi over 2 plus pi n. The range is the same as with a cosecant, and the intercepts, we do actually hit the y-axis at 1. Okay, so that's a graph of our secant. All right, so then cotangent. First of all, let's just review the graph of the tangent because it's been a very long time since we even graphed the tangent. So I have all my values again from my unit circle. And remember, tangent is undefined at pi over 2 and 3 pi over 2 because you're doing the sine divided by the cosine, and that's when the cosine is 0. And so we have these vertical asymptotes here. And then if we were to plot the points in between, so we plot 0, 0, and pi over 4, 1, and then 3 pi over 4, negative 1, and then pi 0, and then 5 pi over 4, 1, and so on. Remember, you got these little branches here in between. They almost looked cubic. Ugh, I should actually go through points. And we'd have the same thing here. If I back this up, I would have a point at -1. Okay, so they kind of looked cubic in between, and they just kept repeating as well, right? They just would hit there. All right. So for a tangent, we had said before back in, I don't even remember, chapter 2 or 3, that the period was not 2 pi, but pi, right? It took pi units for one cycle to repeat. So now if I flip these around, when the tangent is 0, my cotangent is going to be undefined. And this is going to be 1. Now, when my tangent was undefined, if I flip that around, it was undefined because it was 1 over 0. 0 over 1, it would actually equal 0. Okay, so whenever my tangent is 0, it's undefined. If it's a 1 or a -1, those are the reciprocal of those just stay the same. And then when my tangent was undefined, now it is equal to 0. So my asymptotes are at now 0 and at pi and at 2 pi, really the same asymptotes I had for the sine. Now for this one, I'm not going to graph them on the same axis just because it would get so muddled with already the asymptotes that I have and the graph I have. So I'm going to plot this on just a separate one. I think will be a little bit easier. Okay, so my asymptotes are at 0 and at pi and at 2 pi. And I could go backwards, it would be back here at -pi. And then once I have that, I can kind of plot in between. So now at pi over 4, I'm at 1. And at pi over 2, I'm at 0. And at 3 pi over 4, I'm at -1. So when you're comparing these, it's kind of just, it's like it's flipped almost, right? So this branch right here, instead of being like a cubic that was increasing, it's like a cubic that was decreasing. Okay? And then I could keep this going. So at 5 pi over 4, I would be at 1. And then 3 pi over 2, I'm at 0. And 7 pi over 4, I'm at -1. You can kind of see, like if I had tried, and I can do this over here too. If I had tried to graph this all on the same axis, it would have been a little bit messy. Like if I tried to get them on the same ones. That's why I opted to do this separately. But again, similar shape. I know mine kind of look a little weird just because this marker isn't great. It should just be approaching my asymptote there. All right, but you get the idea. Okay, so for my, let's write this here. For my domain, okay, all real numbers except for, okay, it's the asymptotes are at the same place as the sine, so pi n. Okay, so then if I want to do asymptotes while I'm at it here, it's x equals pi n. Okay, my range, my possible y values, it just goes up and down forever, is all real numbers. If you want to write interval notation, you could write -infinity to infinity. Intercepts. Whoops, I can't spell here. Intercepts. I do have x and y intercepts here. I have no y intercept, but my x intercepts are happening at pi over 2, 3 pi over 2, 5. It'll keep happening. So it's happening at that idea of pi over 2 plus pi n, comma 0. Those would be my x intercepts, and my period, how long it takes to complete one cycle, would be pi. So notice that's staying the same with all of them. The period of the parent function is going to be the period of the reciprocal function. And so you might be asking, well, what exactly do I need to know about all of this? Like, what kind of questions are you going to ask me? I do think that you should be familiar with, like, what's the parent function? What's the parent function look like for each of them? I think that's important. But as far as, like, you know, what type of calculation you might do, it would be things like this, right? And you could use your graph for these, or you can really, what I think is easier to use is the unit circle. So if I wanted to use the graph and I wanted to know solve this cosecant of x is -2, that means at what angle on the cosecant graph is the y value -2? So I could come over here and at -2, I could try to figure out, okay, well, where on here, what are these angles that correspond to this? But it's kind of hard to tell exactly. just because it's not a perfect exact graph. So what I think is easier to do is to just use the unit circle. So for the cosecant of -2, I know cosecant is the reciprocal of the sine. So if the cosecant is -2, then that means the sine of the angle must have been the reciprocal of -2, which is -1/2. So I want to know really the angle where the sine, which when you look at the unit circle is the y value, is -1/2. And let's say for these, we want to give our answers from 0 to 2 pi. So that means it needs to be in radians and just where we see it on the unit circle. So a y value of -1/2, y value here and here, and the angles are 7 pi over 6 and 11 pi over 6. Okay, this one says the cosecant of x is the square root of 2. Okay, so if the cosecant is the square root of 2, that means the sine is 1 over the square root of 2. And you might be thinking, well, I don't see anywhere on this unit circle with a y value of 1 over root 2. Remember, usually we don't write our radicals, our fractions with radicals in the bottom. So we call this rationalizing the denominator. We multiply the top and the bottom by a giant 1 of root 2 over root 2. So this is really when the sine of x is the square root of 2 over 2. So I want to know at what angle is the y value, the square root of 2 over the square root of 2. So that happens here and that happens here. And these angles are pi over 4 and 3 pi over 4. All right, so this one says the cotangent of x equals root 3. So cotangent is a reciprocal of the tangent. And then that would be 1 over root 3. Is the tangent, but again, you might be thinking, well, I don't see that on my unit circle. So if we multiply the top and the bottom by root 3, I want to know at what angle is the tangent root 3 over, this would be root 9, which is 3. And I see a tangent here of root 3 over 3 and a tangent here of root 3 over 3. And those angles are pi over 6 and 7 pi over 6. Okay, and then finally for this one, secant is the reciprocal of the cosine. So that means the cosine must be the reciprocal of -3, which is -1/3. And it's an x value. Cosines are the x values around the unit circle. And I definitely don't see a -1/3 for an x value. And so then what you would do is you could just solve this. You need a calculator. So you could actually here, if you kind of recognize, if I take the reciprocal, that's not on the unit circle. What you could have done is taken the inverse secant of both sides and just gotten that answer from the calculator. Or if you'd set this up, you could also have done the inverse cosine and whatever that value is. I think it's 1.9 in radians, then that would be your answer. So there will be cases where you can't find it from the unit circle and you use a calculator. Now, depending on the calculator you're using, most scientific calculators do not have the reciprocal keys on them. They only have sine, cosine, and tangent, so you would have to think of it like this. The Inspires do have, and the Trig functions, they do have the inverse secant. And if you're using the Desmos graphing calculator versus the Desmos scientific calculator, it also has that option. Okay, so that takes care of reciprocal functions. Have a good day.